Hi. Um, so just a quick reminder that I think your assignment, which is graded, we will do the next week, right? 10th of October. The TA have said that you can only submit once, so that it means that if you want to submit again, you have to email the TA, okay? Because of the system, if you submit many times, then he have to sort out many things, or he don't know which one to grade, right? Or you have to tell him he only grade the last one. But to make it easier, you just submit once. But if you really want to do it again, then you have to email TA, okay? But otherwise, like what you work, right? You shouldn't be submitting many times, right? So I think it's okay you submit multiple times, but I would say you would try to submit once. But if anything, you can just ask TA. I think our course will have like 4 to 5 assignments, maybe 4. I mean, it depends. But it will be just make you to work a little bit harder. Other than that, let us continue our journey on random variable. And I would say, as some of you may experience, that it is something that when the first time you learn it, it's not easy to digest quickly. Okay, so I would go slowly today because our goal is to finish this quick. Okay, maybe if time we do code continuous, but it's not a goal. Continuous be next week idea. So because I think we're still in the schedule because this is the first half of the material. So we can go slower. I mean, we'll make sure that everything is fine. So don't worry too much about things. I mean, in case we don't have enough time, we just cut here and there, make sure that everything is covered. Okay, so it's not, don't worry about that. It's good to have deep understanding rather than I just rush over many topics. So the main idea, just to repeat, is okay. Just to repeat, the one of the main reason that we do random variable is it's hard to describe probability, right? Because you have a very complicated random experiment, right? The future can be described in many different cases, right? Imagine a case you have, say, you have thousands of stocks in the stock market, right? And you to describe for each stock, then what is the behavior, how much trading he do, right? So it's very difficult, right? The whole data set is very complicated. Look at financial data, right? You can go to minute by minute, time by second, and so on and so forth, right? So when we look at financial data, often the time look at daily data, right? You already summarize the whole day development into a single number, right? But even by that, it's still very complicated. So usually you look at, right? Your boss asks you, how's the stock market today, right? You would look at the stock index, a single number to represent the uncertain world, right? That's the idea, right? The random number is, instead of looking at many complicated outcomes of the world we want to study, instead we look at a particular number just to summarize the outcome, right? The idea, like, right, if you have a toss a coin, right, instead of taking head or tail, but you only count the number of head or number of tail, right? You count some number. Just then in that case, of course, you reduce the complexity, right? The most easy example is example 2, right? You have 2 coins to be tossed, right? Then the possible outcome depend on the order the head or tail realize, right? In that case, head, tail, and tail head are different in terms of if you record the outcome of the world, right? But if you only care about number of heads, right, then only you have 3 choices: 0 head, 1 head, or 2 head, right? In that case, then it's like this kind of mapping, right? Is the left-hand side is the outcome space, right, or possible outcome, right, if you don't want to use the word space. The right-hand side will be the support or the random variable, what it can be, and then you can see there will be a what we call many-to-one mapping, right? It's just like there are many possible outcomes, but can be mapped to single number. Why it's useful? Because we reduce the complexity, right? You can imagine the left-hand side can be super complicated, but what we care is some measurement, right? This right-hand side, right? And people said, right, or I may not fully agree, but you can taste it is, right? If you can't measure, that's not there, right? So if I can't see it, then it's not there, right? So it's like, if I can't measure it, how can I form probability, right? Something I can measure. So you can imagine that I can count, I can measure, then it's a random variable. Okay? And depends on what number you can map, you can assign to the outcome. If the final number of them is discrete, if infinite number of them is continuous. And of course, you may say the world is finite, right? A very large number, but finite. But why we still is continuous is the fact that, and I'll probably also learn calculus or other math subject, is it's approximation using the continuous easier actually to calculate than discrete sometimes. Although the math too seems to be difficult to learn when you first learn, but actually when you do derivation, actually continuous easier, right? Actually, you will see the bell curve, right? The normal one actually looks complicated in theory, but when you calculate, it's much easier, actually compared to the discrete binomial, actually, last time when talked about at the end of the class. So that would be the idea, okay? So, and if you look at finance application, many application, normal is very commonly used, right? Either the price is normal or the return is normal. Usually we look at the return is normal, but if return is normal, then the price is not normal. But we're not going to talk about those complicated things. But that would be some idea like that. Okay. So let us talk about the discrete random variable. Because just to remind you what it is you look at the world, uncertain world, we only care about the world can represent numbers, and the number are discrete. Okay, that would be the thing. And here we want to give you how you want to can describe, right, the uncertainty, right? Then that is the probability mass function, PMF or PF or PDF, whatever you like, right? But this basically because now your possible outcomes are represented by numbers. The big P is just telling me that you give me a number, I give me a probability, right? Then it's a complete description of the world you want to study, right? Because you tell me the random variable equal to 1 is probability 0.1 and so on and so forth, right? Then you would you'd be able to say what's going on, right? For this example, this is a very nice example because I have a most simple case. I have a toss a coin, on head or tail, right? It can be fair or unfair, but let's make easy case is fair coin. And the outcome can be head or tail. And your random variable only cares number of head. So basically, tail map to 0, head map to 1. Oh, that's random variable, which is this third bullet point. And if the coin is fair, then what we know the PMF or PF or PDF, right? That would be this table, okay? This is the complete description of what we know about the random process, right? And do remind yourself that axioms we learned in the previous class would tell what are the appropriate P then you can do, right? You must be apt to 1, right? And add them, then there's axiom 0, axiom 1, right? It must be 0 to 1, right? The sample space was 1. Adding all the outcome are mutually exclusive must be the same, right? Because number must be mutually exclusive. X must be a 0 or 1. Cannot be 0 and 1 at the same time, right? So they're mutually exclusive. So this would be the description. And usually this mathematical way, right? So usually you want to present it in the graphical way, right? This is the graph to tell you that X is 0 is probably 1/2, 1 is 1/2, right? And a very special thing that I would say special because you will learn another way to describe the P is to use the F. And do remind yourself this is a kindergarten idea, right? Just like stacking the toys, right? Instead of looking at individually, you stack over it, right? There's a big F. And do see that it just, the graphical is easiest, right? Just like, well, it should be blue, but I don't know why. You can see here, this is blue, but I don't know, here become black. So maybe they're colorblind to the projector. So that would be the big F. Sorry. Right here. So that would be the big P and big F. Okay. So if it's more complicated, right? You have toss a coin 2 times. Of course, black. Okay. That would be this thing, right? Because toss a coin 2 times, it can be no head, 2 head, and head, tail, tail, head. If it's a fair, there is 1/4, 1/4, 1/2, right? So that would be the case. And then you can stack them, then you become big F. And if you back stack, then you will be okay. Okay. So now you have to roll a die of 6, right? If it's fair, then you will be 1/6 for each P because it's fair, right? And it's big F will be just going up, right? Okay. And now we have the P or F is a good way to describe, right? But of course, this is good if you have a number of outcome is very small, right? When you have a lot, then your life is a little bit more complicated, right? Maybe very complicated shape, right? Need not be a single, need not be a bell shape, can be any shape, because as long as it satisfies the 3 axioms, it's valid, right? And what is actually P can be depend on the real world data, so you can't really say, right? And so the what you learn from topic 1 is if you want to summarize something, right? If a bunch of data, the easiest thing is to consider the case where you have mean, right? So you can imagine the case where you have the random experiment, right? Each time you run, you have a number, right? Because it's random variable tells you. If you repeat many times, that means that you have many, many numbers, right? When you have many numbers, then the good thing is it's data, right? You want to tell me what's the number is the average, the mean, right? So the mean of, well, so many people come in now. If you want to look at the mean of these numbers, that is called the expectation, right? It's just like whatever value multiply the probability add up, then you're done, right? This is actually the weighted average, right? Because the X will have higher value if it's more likely to appear, right? So just to remind you, it's just use example the easiest, right? If you toss a coin once, right, you have calculated number of heads. All right, if the coin is fair, if a 1 million times of tossing, right? If you have head, you say 1. You have a 0, you have a tail, you have a 0. Then you look at how 1 million toes, you have a bunch of 1 and bunch of zeros, right? And if the coin is fair, you should expect 500,000 are head and 500,000 are tail. Then you have 500,000 1 and 500,000 0, right? Then average will be add up 500,000 of 1, 500,000 0 over 1 million, because that is number of time you toss. So at the end of the day, you get 1/2, right? And did exactly the expectation and the definition, right? So basically, just like you can imagine, you just do the experiment many times, right? And then you just each time you convert your outcome to number and average those number, and that will be the number you expect, right? That will be the number that we do calculation. And I hope you still remember what is the most common application would be finance investment, right? The expectation will be the expected return, right? What possible return, and then that would be the one we care, right? When we do investment, right? Or expected price. And that example, you have CO1 choice, and both of them is 1/2. Then will be just you multiply vertically, right? 0 times 1/2 and 1 times 1/2. Okay, and add each column together, right? You multiply it, and that is what you get the answer. Okay. Same, if you do the same, right? You can see what you do is multiply X, the first row over the second row, and add them every column up. That will be the answer. So operationally, there's nothing deep here, although we have a summation notation, which some of you feel uneasy, but that will be just for each value X, you just multiply. Just you add up along the column, right? The summation sign, sigma, this sigma sign, okay? And we call mu, okay? And So here is one nice property of our expectation. Why it's important? Because there is an understanding of finance, right? When we learn finance, we learn why we care about return. Because return is not nothing we care. We care about the profit, right? Why we care about return, which is normalized, right? It's just percentage, right? Why we care about that? Because there's no difference of talking about return and the profit, because linear, right? Suppose you have invest a stock X, right? X is return percentage, right? It depends on how much you invest. AX is the profit, right? Expected profit will be just A times the expected return. That's it, right? You don't need to really care about the whole thing, right? In terms of expected return, right? So say A is 1,000, right? Then just take it out. And same if you try to have something that is unrelated, is B is a constant. So you say your X is an investment return and B may be the return from bond, or B is not changing anyway. So then just add up. So linear. So things get simple, and you will need them when you do a finance class. And also we simplify a model, right? We don't have need a separate model to model, and we do a random variable for investment for 1,000, investment for 2,000, investment for 3,000, right? You can just focus on the rate of return, right? As long as this satisfies in your real world data, right? That should be all right, right? And you will see some example in assignment, right? Say suppose for insurance company, say, right? X may be percent number of people who get sick, or number of people with disease, right? And A may be each patient you need to pay how much, right? Maybe by your policy, you have to pay $1,000 for something happen, right? Then the case, then how much you pay out is just 1,000 times the number of people who actually have to claim, right? And the good thing is for insurance company, you don't have to worry about how much to pay, right? You look at the rates of people get sick, then you're done, right? So you don't have to worry about many things, but much more simplified. All right, so you will see from the assignment that how we apply this. So as I repeat again, our class, of course, is not math oriented, but every argument we make is math. So there's no way that by listening to my class only, you fully understand whatever we said. You have to actually work out the assignment problem, and you have time to the quiz. The quiz is not credit, right? So you can do it on own pace, or you can pick up whatever textbook or internet resources to work on, because this is basic statistics. So it shouldn't be a problem to find out what are the assignment available. Okay, so the example is like this, right? Is you have a share, the price of stock, right? Can be 1, 2, or 3, right? With some probability, you can make up this number, and usually how to make up this number, it come from data. Okay, we don't talk about in this class, but when you do probability modeling, this is coming from data. So then come from, I make it up, right? You come from data, you can tell each day how likely the price move up and down, then you can estimate those. Okay, but if this is the case, then this is the expected rate of the stock, and then you can calculate your portfolio with 100 shares of the stocks, and bring the cash, what will be the expected payoff, right? And of course, the first thing you learn in the class that we do the descriptive statistic is besides mean, you have variance, right? So here you can see with also the same, right? The reason being that mean is just telling you where the middle of data is, all right? But the variance will tell us how representative of this data is this person, right? So we want to see how good the mean is the variance, right? And in terms of finance, right, that is what we said, right? Is variance is the measure of risk, right? So basically, it's the central tenet of finance theory, or asset pricing, would be say there will be some trade-off between expected return and the risk, right? There's no free lunch, right? So if you want to have high expected return, you need to have higher risk. And how high you want to go for each or one or other depend on case, right? But that would be the thing, right? That's financial planning. They will tell you, right? Look at the client, how likely he accept the risk, and then recommend what kind of product they're doing. Okay. And you guys may not know if you're working, you have MPF, the retirement fund there, right? They will give you different fund. Different fund have different expected return and different risk, right? They also have historical return, then you have some idea what's going on. All right, but that would be the case, right? And the variance calculation is like this, right? For each column, right? You take the X and minus the mean and square and times probability. So this is nothing new, but the formula. So I'm not going to talk about more, but when you go home later with assignment 2, then you can work on those, okay? So one special thing is if variance of risk is a measure of the risk, okay, which is appropriate. For those in the Zoom, you may not aware, I stopped because of the I know wireless transmitter has no battery. So the variance, if you multiply by A, then it will be A squared. So if you double your investment, your risk is not double. If you look at the variance, it's quadruple. Of course, if you take square root both sides, it become variance the same. So it becomes standard deviation, right? Standard deviation will be just still linear in that sense. But variance is usually what we use as a measure of the risk because variance, as you know, is square. So if far away from mean, you would much bigger, right? You take square. So usually we would think variance is a better measurement. But of course, if you rely standard deviation, there's no difference, okay? But the calculation will not surprise you is your risk, your portfolio with stock and government bond will be same as the stock because the government bonds are supposed to be no risk, right? And you're the same, right? If you're 8 times of the stock plus government bond will be just the same, right? Take A squared. And this is how the same problem can calculate the risk of portfolio, right? Imagine if you have 100 shares of X and $300 of cash, right? And the public question would be, that would be something you would do in the investment class, is you have to decide what is the mix of the stock and cash in order to achieve certain objective, right? Achieve some certain required return, and the risk is not above the limit, right? So that would be something. But here's a question here, and there's something I briefly go over, but we don't go to the detail. But we assume that is the case. Okay, that is a bivariate random variable, or go to more random variable, right? Instead of one, you can look at multiple random variable, okay, which is the following, right? Suppose you invest in 2 different stocks, right? 2 different stocks would have a number, right? Different prices, different return. So how can you solve this problem, okay? And you can also describe 2 numbers by telling me that each combination has some probability there, right? Suppose X can assume value of, right? Usually you give a table in the same manner, right? Something you have this, right? Suppose X and Y, right? X can be value of 1 or 2, Y can be value of 3 and 4, suppose, right? You have to tell me that, say, when X is 1, Y is 3, maybe 0.1. This may be 0.2, right? This may be 0.3, right? And remember, you must add up to 1 here, right? So this must be 0.4, right? So this is what we call the joint probability distribution, right? So this is the way you describe it. Because you have to, because X can be value 1, 2, Y can be 3, 4. You tell me all possible combination of X and Y, right? Then every actual calculation will go forward. I don't want to talk about marginal or the other, because we are actually not asking you to know it, but you can easily see that can be extended to bivariate or multivariate without any problem. Okay. The reason that we didn't do it is because we assume things are independent in our application. So that means that we can study them separately instead of doing jointly. So that's why we are lazy, because of, it's not because we don't want to study, because of, if you assume there's something related, then it's much more complicated in math. And we're not math class, so we just assume X and Y are independent, right? It's not the case here, but if the case is the case, then we don't have to worry about things, and we can look at them separately, right? Because independent, we can do things one by one. So that's why we're lazy, right? In here. But do note that because of, if we assume independence, why is the case? I said easier, because if they're independent, right? Of course, regardless of independence, this property holds. You don't have to assume independence. In general, this holds, right? The return of the stock and the bond will be just add up, okay? So when I calculate return, you just don't have to worry about how they're related, okay? Even they're related, the return will just add them up, okay? The only trouble is when you talk about the variance or the risk, right? And if they're independent, say risk of the bond or stock, if they're independent, which is sum of the risk of the term, there's no need to worry about thing if they're not related, right? So just risk of the portfolio will be portfolio of stock plus portfolio of bond if they're unrelated, right? But the fact that the risk or the variance is not unrelated, right? So you have to have a very complicated formula like this below here. You have to add back how they're related, right? And you can imagine, just to make sense of this formula, which I'm not requiring to know, but just let you know in case you go to the investment class, is the fact that if you have covariance negative, right, your risk will be lower, right? Because variance of risk. Why? Because covariance negative means is one go up below the mean, the other one go down, right? So it means that if stock goes up, the bond goes down, or the stock goes down, the bond go up. So the total return, the portfolio return, will be much less variation, right? Because when one go badly, the other one has to go up, it cancels out somehow, right? So the risk is actually lower when you invest in the things that are not moving in the same direction, right? So that is the classical investment wisdom. People will say, don't put all your egg in the same basket, right? The reason is you put the same basket, the covariance is 1, right? So this thing will be the biggest, okay? And if you diversify, right, then you have less risk. And that's the reason why people are willing to pay for financial assets that is unrelated to the stock market, right? Say in the US, people want to buy antique, want to buy art painting, want to buy cryptocurrency, want to invest in Japan, because Japan safe haven. And used to be people invest in mainland China, the A share, which to be unrelated to the US stock, right? I think now the new safe access is in Middle East, but probably now the war, I don't know, but it has been like this. But now maybe India, people think India is safe because of far away from any conflict. But I don't know. I mean, I don't have the crystal ball to tell you what is safe as in the future, but at least in the past, this has been done in this way, right? Or people invest in Australia because, right, that's far away from anything, right? So there's some risk premium have from there. But so as I said, these are a little bit more complicated, but as I said, we will focus on everything is every random variable is independent, so we can do one by one. Okay, so that is same as we do random sample, we draw every sample is independent. Okay, so to make our life easy. So if you want to look at things that are correlated, which you have to do in finance anyway, that would be something you learn in the higher level classes. So in a class, we assume no matter how many random variables we have, they're independent. So our life is much simple, okay? It's not saying that this is sufficient, but for our introductory class, that would be good. You go to finance, then everything will be correlated, right? Otherwise, finance is too easy, right? And for discrete random variable, what we want is to learn some special cases. Actually, I would not say it's a special, or I think it's a more general case. It's some model that would be useful, right? That would be fitting a lot of application in our thinking, okay? Uniform, as we discussed last time, is the first run assumption if you know what might happen, but you have no idea, you have no model, you have no data. Uniform will be the first run to do, okay? And we don't teach in this class. You can combine the base rule to learn from the data to improve your model. So that will be uniform with the first thing, the prior. Your data fit in, posterior, and you update, and then you update, then become your model. Okay, these are the model that usually you would do it at the benchmark, and then you keep updating. You learn new things. Okay, so that will uniform. And Bognoni is the building block for binomial, and binomial is building block for Poisson. Hypergeometric is related to binomial, but you will see the difference. But they are always similar anyway, so that's why we learn it, and they have a lot of application. If you are from accounting, auditing, the hypergeometric will be the thing that you do, or you are the working for quality control. Hypergeometric will be your friend, and Poisson will be things we try to model with time. How many customers come in the next round? This kind of problem, okay, with the time. But let me go to the concrete cases to make sure that this is okay. So this is the uniform. You have n outcome, and each outcome is likely equally. So it's 1/n for each one. Okay, I don't put a number there because any number is fine, right? So it is more general. Okay, so this is, as I said, usually just for teaching or as a baseline before you do an update, right? But I think this is the more important is the basic is the Benoni. As I said last time, Benoni is, of course, invented by Benoni family, right? So they invent that. So basically, you consider the world has bipolar world, right? The world has two possible scenarios, no matter how complicated, it's success or failure, right? Or you can imagine stock market is up or down, bear or bull, okay? Or it's like pancake, in or out. You don't care how it get in or how it get out. That doesn't matter. Or the stock market is up or down. It doesn't care how much it go up or go down. Just two things. Okay. And probably ask what happens if you have more than that. Yes, they do, but it's not beyond our class. Okay, it can be done, but not the purpose of a class. So you have success or failure. Success upon P, failure 1 minus P. Okay, P can be 1/2, but or can be anything from 0 to 1. Okay. And our random variable in this bipolar world, okay, it's just how many success you have, 0 or 1. Okay. So that means that this table, x01 px1 minus pp is a complete description of the world, right? There's nothing new here. There's something very simple, right? Bear with me, it's very simple, but when we play around with it, then it can be very complicated, okay? But this is embarrassingly simple, right? It's two choices, right? Just toss a coin, but the coin may not be fair. Okay, use a coin to think about the world, right? Okay. And the important thing is because of that, we know how to write the big P, right? And the way we write is very mathematical, technical. You wonder why we do that, okay? But it's very natural when you look at the binomial, okay? But you can plug in the number x equals 0, which will give you 1 minus P. If you put x equals to 1, it should give you P, okay? You should be able to see that because whenever anything raised to the power 0 should be 1. Anything that raised to the power 1, that will be itself, right? And The mean will be P, which you can calculate, right? Just multiply the column and add them up, right? And the variance you can also calculate, right? Just each outcome minus P square multiplied probability there. You can check the proof if you want to, but I don't bother that with you. But you do notice that this variance will be the highest when P is 1/2. When P is 0 or 1, that will be no variance. Okay, just to explain again, if P is 0, there's always failure in the data. So all the number you have is just 0. So there's no variance, right? The expectation is also 0, right? If the P is 1, right, every time you success. So every number you get is 1. So that's why the mean is 1. The variance is also 0 because everything is 1. There's no variation, right? The only time that you get the most variation is P is 1/2, right? So you don't know it's 0 or 1, you're half of 1 and half of 0. That gives you the highest variance, okay? So there's nothing new here, just toss a coin, right? So you will see, okay, that's so simple, right? So what are we doing? So now we come to something, have you twist your head a little bit, is what we call the binomial distribution, okay? Which is saying that you, instead of looking at one case, actually you have n different cases, right? You toss a coin, the same coin, n times, okay? You look at success or failure, look at the stock market, right? Each day go up by P, success, go down 1 minus P. Instead of looking at one day, you look at 1 week, five trading day. For 5 days, how many days you go up or go down, right? And for 2 weeks, how many you go up and go down, right? And if you learn technical analysis, that is, if you count 3 weeks, how many times you go up and go down, it's called the relative strength index, RSI, if you learned it, but otherwise, there are application for those. So what we want is look at this thing is like I have look at n different coin toasting, how many times that I have success, right? Just repeat the binomial, right? So if you learn combinatorics, that's what we learned at the end of the last topic, that will be this probability, okay? You ask why, okay? The thing is, there are many, many ways to achieve X success out of n possible trial. That is NCX. The reason is you can imagine the n balls. You have to pick X ball there, right? Each ball have, if you draw it, it means that this is a successful outcome. So there will be NCX, which is this guy, all right? And you ask why is this case? This is the case where the, say, you have the first X time success and the remaining all failure. So that means they're independent, so you can just multiply. So it's P times P times P times P, right? And 1 minus P times M minus X, right? Why multiply? Remember, I mean, it's good to go back to here because they say we need actually a proof, right? Because we can't just say something just saying, right? That is that's to remind you why you learn this definition. If they're independent, probability A and B is just probability A times probability B, right? Probability you have success and success. It's just probability success in the first time times probability success second time. So that's why P times P. You don't have to worry about whether it's success the first time, doesn't change anything, right? So that is the reason why this works, right? And this is in first X success and then all failure, but you can rearrange them. Then that means that NCX, because you can imagine, you can draw a probability tree, and then you see why this is true, okay? Of course, I'm pretty sure that not everyone will understand this, why this is true, okay? When I learn it, I don't understand. I mean, it take me 1 week in the library to figure that out, okay? Maybe I'm dumb, but maybe you guys are smarter than I do. I can see many people very smart, already know very well, but when I was a student, actually, what's that? I mean, it did take me quite a while to bend my head to why NCX related. Okay, I can definitely understand why PX, 1 minus P, NX, because independent, right? I have X times success and my M minus X not success, but why is that? But your head have to be treated a little bit to understand, okay? That's why no wonder, that's why when you look Olympic math, right? in the primary school, they all look at combinatorics. Because you have to really bend your head to understand. But anyway, our class is not math class. If you can't bend your head, that doesn't matter because we just need the formula, right? You just assume that this is okay, right? Because there are so many things in the life you need to understand, but you don't have to, right? For it to work, right? So if that's the case, then we have the mean and variance here, right? So mean is NP and variance NP times 1 minus PY. Okay? The answer is two things. One, each one is independent, right? So each outcome is P, right? Mean of all random variable is adding one up. So that's why it's NP, right? First one is P, add up is NP. So it's the linear property of expectation. The second, because independent, again, you apply the linear property, right? Variance of the sum is sum of variance. So each one is P times 1 is P. So n of them is NP times 1P. Of course, they improve it, but that would be the quickest proof, right? Because this apply the linear property of them, right? Do remind that because why you can just, why variance of sum is sum of variance is because they're independent. Otherwise, this property is wrong, okay? Now, this is, if you look at the graph, it looks like it's a look like bell, right? If P is 1/2, the red one, it looks like a symmetric bell. If P is not so nice, it looks like it's skewed bell. So you can see by changing N and P, then N all shape can be accommodated, right? So one thing that you would might have time to, but don't have time to learn, but you can imagine, you can see that if there's a data you have, you can try to figure out what the best P to describe the data, right? Then you can, this will become your model, right? Your data tell you this shape, you try to figure out what's N and P to feed it, and then this becomes your model, right? Because you have a complicated data. You reduce it by simple model with two number, N or P, right? Then you can do prediction, right? But that would be way beyond our class, but that is called probability modeling, right? But because some of you may ask why we have to learn all these things, right? So maybe I talk about this final example, have a break. Sorry for a little bit delay because I think it would justify why we all want to learn this, okay? So imagine maybe you are working for Indian restaurant owner, right? You look at spicy food or Sichuan restaurant, right? So you figure out that 30% of the customer like spicy food, okay? So maybe he do a survey, whatever. The question is, okay, now he have a 5 customer coming in, okay? Then he want to see what's probably 2 of them like the spicy food. Okay, you can find 1 up to 5 or 0, right? You can find a number there, but focus on case 2 customer like it. Why he want to do that? Because maybe he want to say how much food to prepare, how much spicy food to buy in the morning, right? So there are 5 customers who like it. So how do we do that, right? So you have 5 possible trial, customer independent, right? Each, basically, I toss 5 coins, okay? Or toss a coin 5 times, right? Each customer is a 5, is toss a coin. The coin is a bias. 30% he likes the spicy food, 70% doesn't, right? You toss a coin 5 times. The question is exactly 2 like spicy food, right? Exactly the coin toss is successful is 2 out of the 5. So that is binomial, right? Because you have 5 trial, right? Independently. Each coin is tossing independently and the same coin. So that probability of 2 is 5C2 and 0.3 raised to the power 2 and 0.7 raised to the power 3, right? Because P is 0.3, 1 minus P is 0.7, right? X is 2, right? And 1 minus N minus X is 3. So that is how we get this number. Just to remind you, this is N, right? And this is X, right? And this is P raised to the power X, right? And this is 1 minus P, and this is N minus X, right? And this is done. Okay, this is how you do this calculation, right? So you can ask yourself, what happened is 3 of them like spicy food. The same formula, but X becomes 3, right? So you can know 0, 1, 2, 3, 4, 5. You can do calculation rather easily, right? You don't have to worry about things. I mean, if you doing your assignment 1, you will see you can apply this quickly to calculate. If you toss a coin, I think 4 times, 5 times, I don't know. And two of them are head. They actually can have that easily. That's a binomial. Okay. And I guess let's have a break of 15 minutes. In the meantime, you reply. I think I convinced you why we need that. So if you have time, please feel free to fill in. So I think it's time so that we can look at what is the response to this, and then see the how well we're going. Don't understand the graph of binomial. So let me explain. Okay. So the graph is like this. Remember, this is P of X. Okay. Tell us that for each number, what are the probability, right? Suppose the case we have n equal to 6, the red one, p equal to half. Okay. So according to the formula, actually there's something with this. We already tell you, right? If n is equal to 6, p is half, it will follow this one. Right? Just telling me that, okay, suppose you total con 6 times, how many times you get head? Say head is success, or how many times a head, right? So half of half, right? Halfway, then you can imagine that, I mean, yeah, you expect actually the number of success is actually 3, right? Because 6 times 0.5 is 3. So basically that's why you see the bar, this is symmetrical, the red one, right? 3 is here, 2 and 4 is symmetric because they're the same, right? And then 1 is like the bell shape, okay? And if you look at the case where you have only 4 cons, n is equal to 4, and success is only less than half, P is 0.3, means that you are more likely to fail than success. So that means that your curve is not symmetric. Will be skewed actually to the right-hand side, right? More likely the loop side on the certain one because you're more likely to fail than success. So you can see the bar is like mostly concentrated on 1, right, and 0, right? This is the reason. I'm not sure if I tell you that, but if you look, can imagine if P is 0.8, then we'll be a little bit over the other side, right? So that would be the model. You can imagine this is a bell, more like a bell curve, right? Somewhat, but if it's P is half, it's bell, but otherwise it will be skewed at some level, right? Depend on the P, but something is not something too surprising. I hope. I hope I answered your question, but if in case I didn't, then let me know. Is exam open book? Yes, open book. You can bring whatever, okay? As long as it is anything paper you can bring, okay? But you can't share. Cannot be any obscene, cannot be any anything is legal, you can bring, okay? There's nothing forbid you to bring. I mean, I don't, as long as legal in the school, it's legal for me, okay? As I told you, right, the reason why we have to do the paper open book is because of I have no way to deter cheating. And if one cheat, then we have to take all the exam again. So sorry that I can't be environmental friendly, but I mean, but if you want to environmental friendly, then you don't need to bring any paper, right? So it's okay. Or you can use recycled paper. You can bring your handout. I mean, whatever thing you can bring. You can bring a textbook. It's also okay. I don't mind. It's so cold. Okay. 23, 23, 24. How high I can go? Maybe go up by 1. That's the best thing I can do. Already 24. So I can't go further. Yes, it's the combinatorics. Yeah, it's very interesting. As I mentioned, some of you tell you that in the break, right? Here are binomial. So you can imagine there should be something like trinomial, quadnomial, or in general multinomial. Yes, indeed. You can look at Wikipedia if you're interested, but you can see that not too much different from binomial. So if you understand binomial, everything is very simple. That means that if you have a more than one outcome, success, failure, you have maybe success, failure, or so-so, like 3, then it's very similar. You can also do that. It's not a big deal. But 2 outcome is already good enough for us to play around. Okay. And who is sick? I don't know, but I hope you get well. It's only my daughter gets sick, not me, but I'm okay. So I don't know how about you. Yes, as I said, this class, if I make everyone very clear, then we don't have time to finish everything. I'm sorry, but I try to make as clear as possible. But the big thing, as I remember, the first day I said in the class is make sure they understand the green thing. Okay, understand how green works, then you should be fine. Okay, you with together assignment, then you know how to operate, right? Because this class is operational class. You have to ask a question, you have to operate the procedure to calculate. And to have a deeper understanding, of course, cannot rely on single class to do it, right? You have to go, the expert, you come probability, you have to do other classes. Okay. So I'm sorry you're confused, but if you confused, then easiest to write your question here. I try to explain again because I don't want to rush. Oh, someone still think we are in holiday again. It's Tuesday, but it's Wednesday. Yeah, it's windy, sunny. Oh, it's windy. Yeah, maybe the case. So far it's okay the speed, but someone says 2, so I have to see if I slow down a little bit. Overall, it's okay. So this question is asking whether this class is curve or absolute grading, right? So actually, it's to fit what we are saying, right? So basically, what is asked is whether we fit your marks to a fixed distribution or just a cutoff. The answer is both. Okay, both. This is what actually I understand is what we have a uniform policy in a B school, at least I understand, is we are no longer actually, okay, you can say both or none. Okay, the reason is because we are doing what we call the objective grading approach, right? It's like we have course outline, we have a criteria, we got A, B, C. If you fit the criteria, you will get A, right? But how to quantify that? And usually look at your score. And luckily later you will understand if at last class, usually when we assess you based on your assignment, your project, and your exam, it's very clear that some people are here, some people are there, some people are there. No matter I use absolute grade or relative grading, I mean, no matter what I use, then should be fine. And usually I would do the most liberal grading. So no matter absolute or relative, you get the highest whatever according to two scheme. So you say none or both, but anyway, I mean that's same for every single class. So it's not my class do a particular thing, but historically, I mean, as I said, right, if you get top tier, you will get AA minus, right? The top tier, I think top 30%, and the remaining, the median grade, right? Same as most classes would B plus, right? And then you will get some B and B minus for the rest, and maybe one or two people who just copy exam, don't appear lecture, whatever, sleeping, then probably get C, but otherwise should be fine. If you attempt do all the assessment required, then it's very difficult to fail. I mean, you can try, but I never able to fail anyone. But you can probably try to do it. I mean, if you can try. I mean, it's very hard to fail if you do everything. Okay, if you do nothing, then of course you will fail, right? You don't take the exam, you don't do the assignment, you don't do the project, of course you will fail. But otherwise, I don't see the case. Healthy jokes. Oh, healthy jokes. It's far getting cooler in this tropical rainforest on Hong Kong. Oh, welcome to Singapore, and you know what is tropical forest. Well, I've been there for 7 years. That is actually every day is Sunday and humid. That's where, I mean, if you like it, then you like it. Otherwise, not that fun. I mean, I have a friend actually who based in Hawaii. Then he said, "Oh, Hawaii is good, but he never stays there for consecutively more than 2 weeks. You have to run away because it's so hot, so humid in the island." Maybe you feel the same. I mean, I think Hong Kong is already very mild compared to many places in the world. But it's cold. Hopefully it's okay. I'm sorry that you might be confused, but you will do assignment, you will know. Hopefully I go for more example that can convince you that these are very useful way to do application. Okay. Another example that continue that the example that we discussed before the break will be, we are not interested in x equal to 2, but we're interested in x is 0 or 1 or 2. Or the reason maybe this example is I have a 5 table, right? Instead of one customer, be 5 table, right? I have a in the restaurant, then I would want to see more than 2 of them is like spicy food. The reason why maybe in the fridge I only have the material for 2 tables, right? The question is asking whether I need to buy more or order more. So that is how this question is being designed in my mind, right? So we want to ask the question is how likely that is number of customer like spicy food less than 2. Turn out, of course, you can do the calculation. It's 80%, so you don't need to buy. Okay, of course, the calculation is not complicated. Okay, you will see there's a lot of calculation, but don't worry about it. If you actually work on it, Excel can calculate immediately at a click. Okay, in a 5 seconds you are done. If you do Excel, of course, when you have the calculator in exam, then you take some time, but this shouldn't be concerning too much if you use the Excel formula. If you look at the very end of our slides, Excel can tell you immediate calculate so fast in 5 seconds. Okay, so but you can see how this thing can be applied, right? You can imagine there's something is going to happen. right? Or some outcome you can count, right? And the outcome can be yes or no, right? Then each thing is independent, right? And they're the same, then just use binomial, right? This is very easy to imagine, right? For example, this is something like if you are doing a operation management, you are working for, say, subway company, MTRs, right? And then you can imagine each day there will be maybe 0.1% that a train may become 40, not working. How many reserve train you have to prepare? Or your bus company, right? There may be 1% of, or maybe 0.5% that driver takes sick leaves. Then how many driver then you have to prepare, right? To do the calculation is based on this. Okay. All the engineering operational thing is binomial is so convenient, right? Because each driver getting sick is independent. And you can imagine from historical data, how many of them take sick leave, give the probability. Right? You can calculate how likely that more than 2 or 3 people will get sick, then you can see how many driver you need to hire, right? And how many driver you need to hire to make sure that you have an appropriate level of service. Okay, so this is a rather standard thing, okay? So there are many examples, as I said, right? There's a marketing campaign, right? You can imagine that, okay? You need to reach certain level of, I don't know, publicity, right? Then you want to send the advertising to, say, 1,000 people, right? Then you can assess how many to send, right? To calculate the probability, and then you can do the binomial and see what is appropriate number of advertising campaign you need, right? All these things, say quality control, right? And then suppose you look at 10 product, only 1 product is defective, then you can see whether this is going to be a nice thing, right? You can go back, right? Because same all the HR problem, quality control, inventory management. I'm not going to one by one, but because you can read it because that's English. But now I think this day you have AI, you can ask AI, what is used the binomial distribution in business application? You can have a bunch of them. So I'm not going to go over that. Okay. I just give one particular example to convince you this is good. Okay. And say, for example, you want to promote new product to a target 10,000 customers. Okay. And using historical data, if you get a leaflet, maybe 5% you buy the product. Okay. And you can use binomial and calculate, okay, what's probability that 500 people actually buy it, right? Then it just 10,000 and X is 500, X is 5%. You can do that and calculate the probability. Okay, of course, you can calculate 500, you can calculate any number. Okay, use Excel, can quickly calculate, tell us how it looks like, right? So of course, this is the thing is like very skewed on the left hand side, right? Look at the graph. But that will be the case. I'm not going to repeat all the example, but you can easily check. Okay, as I said, these are technical, so I don't expect you to reproduce this thing in the test or assignment, but just telling you that how this binomial can be applied. Okay, so if you need and reason to convince you why you need to learn binomial, you see it. But if you're convinced already, so you can just skip. Okay, or you can check out why we need them. These are the proof, which I will skip anyway. So next now, go to Poisson, which I would say the binomial and Poisson are the most useful thing, right? Binomial apply to things you can physically count things and each one come out equal likely. Okay, you can divide things into different components and do the calculation, right? And each component is very similar, right? Then you can, and each component can outcome success or failure, then you can do binomial, right? So that would be the idea, right? They say something I don't know in the future can be divided into multiple components, right? And each component is independent and very similar, and the probability of each outcome each component is success or failure, right? You can count how many number of success. That's a binomial, right? So Poisson is actually, you can imagine it's a way to apply to time dimension. Okay, this related to time, the Poisson. It's so convenient that you can imagine this Poisson will be the baseline model when you later, if you go to 4,000 classes, when you learn probability modeling, or called stochastic process, if you like, that Poisson is the baseline. Everything based on Poisson, and I think the limiting case is related to the Bandian motion. If you learn Bandian motion from physics, that is very highly related. It's two-dimensional with option pricing, all related to this, because how things change over time is first thing studies Poisson. Okay. So the idea is very simple. Remember, binomial is what? Binomial is, imagine, as I said, if something, you then cut them into different pieces, and different pieces is very similar, right? And each pieces can either success or failure. Can count how many number of success, right? Over all possible pieces, right? So you can imagine that actually you look at the time, okay? And you cut each time interval is a component, okay? And if you cut the component enough, small, right? And there will be, you can count success or failure, right? To make it more concrete, imagine the following. You are at a restaurant, you want to see how many people coming in the morning, right? Then you can think each 5 minutes is interval, right? So if for an hour you have 12 interval, for 3-hour morning shift, you have like 36 n, right? 36 component. And each component, can imagine the customer comes in with some probability, right? By using binomial, right? With n with 36, p may be 5% as customer come in. Then you can model the time process, how people customer arrival. Okay, so that is what we're going to do here. Okay, let me do a picture here. No. Okay, let me draw a picture to show you this. Okay, what's binomial? Remember, binomial is what? Again, it's a con. Okay, you toss it n times, right? You have. Let me see if I can use this pen. Okay, you have n cons, right? And each con is success, failure, success, failure, failure, success, right? You can count them, and each probability comes out. It's p, right? It's binomial np. So you can imagine in our mind is, I look at a time interval. Okay, I divide it into many sub-intervals. The n of those. Okay, and I would say, will their customer come in this moment? Success or failure? Right? Success means someone come in, failure is not. Of course, if you cut it so small, the probability that come in is very small. P is very small, right? But n is very big, right? So when n is very big, p is very small, okay? You can still do binomial, right? But when we take the limiting case n to infinity, okay, then we have the formula is very simple. Okay, the formula now would become what we call the Poisson distribution, because it is discovered by Poisson. So this guy, right, some number of people who are coming. When you take n is very big, p is very small, because you cut the interval of time into very small. You only allow one people come in every second, right? Although the door at any moment of time you can have 2 people come in, right? But for every millisecond or every second, you can only allow 1 people to come in this door, right? So every moment you only allow 1. Okay, that's a Poisson idea. Okay? Then this will be simplified to even more simple formula, where is e to negative np npx x factorial. Okay, again, this formula is crazy, okay, because Why you have E, you have factorial, all this, okay? There's math behind. It's very genius math proof because you can see this very complicated formula. Why become this? I don't want to answer that, but there's proof there, but the proof in the slide, but I'm not going to prove it. If you interested, you can look at YouTube video. There's a lot of proof, okay? But E is a number 2.718, okay? It's a natural number, okay? And because NP always appear together, and NP is what? Mean of binomial. So we will call Poisson only use one thing called lambda, okay? Because NP is lambda, okay? So that's what we have, right? Nothing new. Instead of working n outcome, each outcome has probably p success. You just n is infinite, and p is very small. Application is time, okay? Look at the graph. You look at the application, so don't worry about that. So this is the formula, right? E like it's a lambda x factorial, okay? And as I said, this class, you don't need to remember formula anyway. So no matter how crazy the formula, you just have to apply, okay? And in application, you have Excel, so you can just do it in 5 seconds, right? When later we teach you Excel, right? But only thing I want to mention is very funny. You may or may not care. Is this model, the mean and the variance are the same number, okay? Which is something super weird, okay? But you don't really worry about that. But later when you learn property modeling, whether your data would fit Poisson, you look at whether mean fits variance. For binomial, if you recall, mean is bigger than variance. Just to be exact, because binomial means NP, variance NP times 1 minus P. 1 minus P is less than 1. So the variance less than mean for binomial. But for Poisson, because P is going to be 0, so this is gone. I think that explains why, okay? Okay, so that is the idea. So there's a Poisson. It's most useful to model some event happen or not, okay? Over a period of time, okay? So let me give an example, then you will see why we need that, okay? But first, look at the shape, okay? Remember, binomial only have one number, lambda. So depending on the size of lambda, when lambda is 2, then it look like this. When lambda is bigger, then you look like much more flatter. The bigger the lambda is, it's really close to the bell curve, okay? So that's why sometimes when you look at things in the grand scale, everything become a bell curve because everything become a very nice bell stuff. But let's look at example. Then I hope to convince you that will be useful. Okay. So this example that is easy. Okay. You can look at this case is you have a number of customer actually follow the Poisson with mean 5. Okay, an hour. So that means that every hour they will expect with 5 people come in, right? And then on average, okay, maybe less than 5 is fine, but looks like bell around at 5, somewhat like that, right? You can draw a picture on that. So the question is, what is the probability exactly 2 would come? Okay, that's very simple. It's P of 2, right? Just plug in the formula there, they're done, right? Because this is lambda is 5, x is 2, just basically this formula, right? Lambda is 5, x is 2, and that's it, right? So I think you can do the calculator quickly. But as I said, later when Excel, this calculation comes out handily in 5 seconds. Okay, so don't worry about the calculation. But of course, you should be able to know how to do calculator, right? So it's very little number of people will come in. Only exactly 2. Okay. Of course, you can do more, but let's look at application to convince you this is very useful, right? So for call center, right? And he want to see how many calls you have in an hour or so, or 2 hours, then you can do the calculation, right? And website traffic, right? You could try to see how many people would come in. You can model that part and decide how many capacity your computer would be needed, right? Or manufacture defect, right? And then look at the time, number of defect in a period of time, right? And insurance claim, as I said, right? All of time you claim for a time, how many people would get injured, right? So on and so forth, right? Or how many typhoon would come in a year, right? That would be a Poisson, right? So you can easily calculate that, right? Shouldn't be surprise you. So now this example, I'm not going to repeat it because this is a very simple application, right? The example like this, I will just go for this quickly, right? So this said a call center receives on average call 50 calls per hour. That is the average. And if under Poisson, that means that lambda is 50, right? That's the mean, right? And then you ask what happened, you have 60 number of calls, there's a P60, just plug in the number, then you're done. Yes. Oh, okay, that's a good question. Okay. You really can't count 60 or more, but you can count 0 to 60. Do complement rule. You can calculate 0 to 60 and then do the rest because this, okay, one of the way someone asked a very nice question is x can be 0, 1 up to infinity, right? So you really can count from 60 or more, then you count 60 to infinity. But the fact that you can calculate 0 to 60 or 59, take the complement rule. So that's why we need complement rule. That is a good question. Why we need complement rule? Because you physically can't calculate that. So have to be 1 or 1 minus. Very good question. So how now we learned two distribution, right? Binomial is you have n different component, each component same, and then independent. Each component is success or failure, right? And then success is P, then you count how many success. And Poisson is over time. You have a time, but you divide into with n different pieces, but you divide the time so small that actually n go to infinity. And each time someone come in is probably P. So an limiting case of binomial, right? So the application here, it looks like the binomial, you do the component independent, right? But sometimes actually not independent, we do things, right? Suppose that is a most common case is we try to take out something, we do audit, okay? You go to a inventory house or warehouse, right? In warehouse, you pick up 5 objects and check whether five of them, whether any defective product, right? That would be something you would do, all right? And you are not going to take it out and put it back. If you do it, then binomial would fit, right? But if you draw something out of it, the thing changes. So each step you're doing is different, okay? Then how can you solve this problem? And this is hypergeometric, okay? Of course, you can imagine that if the warehouse is super big, then you only draw such small number of samples. Actually, there's no difference because very small difference because you draw something from a big pond, draw one fish from a very big pond. There's no change in the composition of the pool, right? But the pool is very small. You draw one fish, things can change rapidly. Okay, so basically, it's like you can imagine this is a binomial, but a little bit you allow some realistic finite sample adjustment. But anyway, let's see the example. Okay, you will see it's very closely to binomial. Okay, and indeed, if you are careful, you can see their connection there. Okay, so the question like this. Let me draw a picture. I hope that will make a lot of sense here. Okay. So the question like this. Here I go to the warehouse. Okay, I know the n object here. Okay, maybe number one here. Okay, maybe not man, maybe this is not a good. There's a good item. There's another good item. There's a good item here. Okay, good item. Okay, and then maybe bomb here. There's a bomb here. Okay, bad item. Okay, so you know there will be out of n item. You know, a of them is good. Okay, and then of course by construction, n minus a is bad. Okay, n is of n, a is good, n minus a is bad. Okay, now this is someone the client told you. So what you're going to do is you're going to draw small n from the warehouse. Okay, draw small n from that. You don't know what you draw, but anyway, you draw n from that. Okay, n from that. Okay, the question is, I want to ask how many of them is good. Okay, x, the question, the random variable is x. X is how many of them is good. Okay, I draw it without replacement, so I draw it, then it's different. Okay, I draw x, I draw n of them, I draw n things out of them, asking x of them is good. Of course, x cannot be more than a because the at most is a, right? So x can be only have the value from 0, 1 up to a. Okay, because you draw all the good thing there, right? Okay, so that will be the question. Okay. So is it clear what we are asking? So let me repeat because it had to be complicated, right? So there's n, big capital N in the warehouse. Someone told you that a of them is good, n minus a of them is bad. Okay, and then you have to draw small n from this. Okay, you close your eye because of random draw, right? The infantry check. And then you're asking how many of them you open it. It's a good. Okay, x of them is good. Okay, so this turnout, don't worry about it. This is not complicated. Okay, it's following this crazy expression, but this is not complicated. Okay, look at the denominator first. N Cn, right? You have n object, big N. You have to take n, so that's n of big N of a small n C way of do it, right? Because n take simple. The numerator is not complicated as well, because you have to draw x good thing, n minus x bad thing, right? Out of a okay stuff, you draw x. Out of n minus a, you draw n minus x. That's it. That's the probability. If you learn combinatorics, we learned in last class, sorry, previous topic, this is very natural. Again, as I said, you are not required to know why this is true. You only need to apply this formula, right? I tell you it's hypergeometric, or why it's hypergeometric, you can do it. Okay? But the formula, I give it to you. I explained already, but you don't have to worry about it. Okay? And perhaps not surprisingly, you calculate the mean is small n over a, big A over n. Okay? But what is A over n? A over n is a closer eye. You only draw one thing. What's probably you get a good object is A over n. So if you close your eye, just the A n or big N of stuff you draw once. It's P, right? So it's binomial NP, right? So that's nothing new here. Expectation same as before. Okay, that's no different. The only thing is variance, right? If you accept this is A over n is P, this is NP, this 1 minus P. You forget this guy, that is binomial, right? The only thing you can look at this is n minus n, right? When n is 1, that is binomial, right? But when when n is more than 1, you can see this guy is different, right? It's smaller variance, right? It's smaller, right? Because this guy is less than 1. Why? Because you keep drawing things, the finite, then the variation goes down, right? Because you cannot, when you draw extreme value, once you draw, then only left is value is less, okay? Sometimes people call this is, when we look at the literature, they will call this finite sample adjustment, right? Because when big N is so big compared to small n, this is 1, right? Look at, if big N is very, very big, this is 1. We take the limit if you want to be precise, right? So let's look at example before we end the class, okay? So this is what it looks like, okay? So it's a red, and this is a blue one, depending on what is n, small n, and big N, okay? But let's look at the example, okay? No, there's example, and then we'll end the class, don't worry. As I said, this is complicated, so we'll repeat a little bit next week, okay? But the example like this, okay, you go to warehouse, you are told that there are 30 computers, so that's big N is 30, and 4 of them are defective, okay? And defective here is something we want to figure out. So defective is A, okay? Success or failure depend need not be real world success, right? Because we want to find the defective stuff. So such A, the big A is 4. The question now is we're asking ourselves is we take out 6 objects there, okay? How likely 2 of them are defective? So the small n is 6 with 6 items, and 2 of the x is 2. So let me repeat, n, big N is 30, and A is 4, small n is 6, x is 2. And you will ask I do this weird notation because this is how we input Excel formula. So you ask me why I have something crazy because this is what number you input in Excel, okay? So this, nothing, just plug in number. Only thing you can see this is you are taking things out, so you would apply the hypergeometric. Of course, you may ask, if you put it back, then it's a binomial, right? Because every time you take it, P will be 4 over 30, right? N will be 6, right? You can also apply binomial. You can do the calculation, but it will be different, right? So it depends on how you draw sample. If you draw something out, put it back, then we binomial, which have N is 6, P will be 4 over 30, right? But now we draw things together and take it, then it's become hypergeometric. So it really depends on where they put it back, right? But of course, if N, the big N super big, there's no difference. Okay. So I hope that I convince you that the lot of application you can do, and I would say these are the main application you will use in application in all many other applications as well. So of course, if you look at Wikipedia, there are more than hundreds of distribution. We only pick up 5 that is most commonly used, and you learn how to apply this. How to apply the rest of the 300 should not be an issue, because it's just different number apply different cases, right? Because at the end of the day, distribution is telling you the structure of the P, how the bar looks like. Okay, I shouldn't take more time than I should. I'll see you next week.